Alright, so now we're going to look at linear systems from a pre-calc perspective, but let's review quickly from an Algebra 2 perspective. You'll remember solving systems like this here. A system is just, a linear system is just a graph that has two lines, and the solution to the system is wherever those two lines intersect. So in this solution, we know, or in this system, we know the solution is -2, 0, and that's if you find the solution by graphing. But remember, finding the solution by graphing was very problematic. If you graphed by hand, there was room for error, and very few graphs actually intersect at lattice points like this. So we developed a method of solving by using row operations that change the value of one equation by multiplication or division, and then added to another equation would help us get our solutions by eliminating variables. And so in this case, if I wrote 3x minus 2y equals -6 and lined up for the second equation my x plus y equals -2, and think about an operation I can do on one or the other of these equations that would let me subtract or add to get rid of a variable. So I think I could multiply this bottom equation by -3, and then if I added, the x would disappear. Or I could multiply the bottom equation by a +2, and if I added, the y's would disappear. And I could do the same thing with a multiple on the top equation, except I would have to use a fraction to get it to be 1 in either case. So I'm going to choose to multiply the bottom equation by -3. So now I'm going to rewrite the whole thing, and I like to use a really fat line so I'm clear where I am. I'm going to write the first equation again, 3x minus 2y, because that's not the one I'm changing, equals -6, and now I'm going to rewrite the multiple of the second equation. -3x minus 3y equals +6. So 3 minus 3x cancels, -2, -3 is a -5, y equals -6 plus 6 is 0, so y equals 0. And in fact, that's exactly the y value of the solution in the graph. Now, to find the x value, I'm going to plug it back into either of the original equations. I'm going to choose this one. So I have 3x minus 2 times 0 equals -6. So 3x equals -6, so x equals -2, and in fact that is the x-ordinate to our graph. So that's all well and good and fine when you have two variables, but what are you going to do when you have more than two variables? And by the way, panic and refuse to do it is not an acceptable answer. Well, let's look at one first to see what the monster looks like. Suppose I have x plus 3y plus 2z equals 5. Now, the only hope I have of ever being able to find the value of x and y and z is I'm going to need three equations. The reason I needed two equations over here to find x and y is two variables, two equations. That's a rule. I need at least three equations if I want to find the values of x and y and z. Luckily, I have two more. I have 3x plus y minus 2z equals 7, and 2x plus 2y plus 3z equals 3. Now, we're going to use a process called Gaussian elimination. It comes from Friedrich Gauss, the mathematician that developed the method, or at least formalized the method. So Gaussian elimination. And in fact, you've done Gaussian elimination before, because when we eliminated this x term or x variable from the first equation or the first example, we were using elimination to do that, or we were using a method of Gaussian elimination. There are some rules. One, you can interchange equations all you want. Let's say freely. And what that means is if I want to rewrite this where the middle equation is written first and then the third equation and then the first equation, that's fine. I can always flip equations back and forth in their order in the list. That's always allowed. Second, you can multiply any equation by any number except for 0. And that makes sense because if you multiply an equation by 0, you make it disappear, and you can't get rid of your problem by hiding it under the couch. You have to actually deal with it. And then third, you can always add a multiple of one equation to another equation. Which is exactly what we did here. And bear in mind that the goal is to get the whole thing in triangular form. And you'll see in a minute what that is. It's also called row echelon form. But that's more specifically related to matrices, which we'll do in a little while. Basically what that means is you're going to have an x plus a y plus a z. This is just symbolic at this point, equals some constant. And then on your second row, you'll only have some value of y plus some value of z equals some other constant. And then on your third row, you're just going to have some z value equals some other constant. So I could call these, well, I don't want to put in a bunch of a's and b's. Just look at it as a shape or a picture. Don't think of it specifically as these C's all have to be the same. They don't. C1, C2, C3. And then it's easy to see. If you know what Z is, then you can plug Z into this equation with a constant to find out what Y is. And then you can plug that back into the first equation. You put in Z, you put in Y, and you can solve for what X is. So that's really what we're trying to do with this system. So let's go ahead and start playing around with it. And there are many different orders to work in. Everybody's going to work a system differently than somebody else. As long as you're following the same steps or using the same rules, you'll get to the same place. With practice, you'll start to see easier ways to get there, but in the meantime, you just kind of have to plug away at it. And notation in this case is totally your friend. So here's the method to your madness. You want to get this corner down here, because what you're doing is trying to get rid of whatever was here, and whatever was here. So if I can get rid of this one first using one of these first two rows, then I can get rid of this one, then I can get rid of this one. So you sort of want to work in that order as you're trying to get rid of your values, of your variable values in various equations. So let's go ahead and first step decide. Well, I'm going to take advantage of number 3, which says that I can add a multiple of one equation to another. So notation matters. To this equation, I am going to add -2 times the first row. Okay, so I'm going to multiply the first row by -2 and then add it to 3. Now, rather than actually doing all of this work over here, because it can get really messy really soon, I'm going to do it in another way. So when I add to this row, this is the row that's going to change. So I'm going to write down my first 2 rows exactly as they are. Just so I resist any temptation to make any changes that I shouldn't be making yet in the middle of the process. Now, my third row is going to be different. I'm going to take it element by element. X times -2 is -2x plus 2x equals 0. that worked. I got rid of this bottom element. And then 3y times negative 2 is negative 6y plus 2, negative 4y. Then 2z times negative 2 is negative 4z plus 3z is negative z equals 5 times negative 2 is negative 10 plus 3 is negative 7. So all I've done now is change my bottom row. Okay, that seemed to work for me. And I'm going to go ahead and erase this because I want it to be empty there and I want it to show up as empty. All right, so now I want to get rid of this element. So I'm going to work straight up. That means I want to get rid of my negative 3. What I did in the last step seemed to work really great. So the notation is I'm going to change my middle row. So I'm going to put an arrow. That's telling me that this is the row I want to change. And I'm going to change it by adding row 1 times negative 3. So I'm going to multiply row 1 times negative 3, and then I'm going to add it to this row. First things first, let's write the rows that we're not going to change. Okay, so the row I'm going to change is that middle row, and I'm going to change it element by element again. So 1 times negative 3 is negative 3x plus 3x, 0, it disappears. Yay! 3y times negative 3 is negative 9y plus 1y equals negative 8y. 2z times negative 3 is negative 6z, take away 2 more z's, negative 8z. And 5 times negative 3 is negative 15, plus 7 is negative 8. Okay, so I've gotten rid of these. Now all I have to do is get rid of this. So let's look at our rows. Well, I could multiply this row by 1/2, so it would be 4, and then, or by negative 1/2, so it'd be a positive 4, and add it here. And I could do that, but let's notice something that I did in my first 2 rows. These rows were so easy to alter because I was multiplying them by row 1, which had a 1 out front. So if it's possible to easily convert this negative 8 to a 1, let's do that. And in fact, it is. I'm going to change this row by multiplying it by negative 1/8. Okay, so let's write the rows we're not going to change first. Oh, you can see I had an earlier effort. So I have x plus 3y plus 2z equals 5. I'm not changing that row. And negative 4y minus z equals negative 7. Okay, the row I'm going to change, I'm going to multiply by negative 1/8. So I'm going to get a positive y, a positive z, and a positive 1. Now, super easy for me to change this third row by adding 4 times row 2. So if I'm changing the third row, the 2 rows I'm not changing, x plus 3y plus 2z equals 5, and y plus z equals 1, and now the row I'm going to change. Y times 4 is 4y, take away 4y is 0. Z times 4 is 4z, take away z is 3z. 1 times 4 is 4, take away 7 is minus 3. All right, now I'm technically done because I have my triangle form, and all I have to do is worry about back substitutions. So let's do it. Well, this last one tells me that z equals negative 3 divided by 3, negative 1. Now if I plug that into this equation, I get y plus negative 1 for z equals 1. So y equals 1 plus 1 equals 2. And now I'm going to plug both of these back into the first one. X plus 3 times y plus 2 times z equals 5. X plus 6 minus 2 equals 5. Probably arithmetic you don't really need to see, but x plus 4 equals 5, so 5 minus 4x equals 1. So these three lines intersect at x equals 1, y equals 2, and z equals negative 1. So in the three-dimensional plane, let's see if I can draw it for you. I'm not usually so good at this. Let's see, how about, well, hang on, give me a second. Okay, where this is the x-axis, this is the y-axis, and this is the z-axis in three dimensions. X equals 1, right? Y equals 2, so in the Cartesian plane you would end up with a point here where y is 2 and x is 1. And then in the z-plane, negative 1, it's going to drop down to the negative 1 on the z-plane. And so you get this floating out in space, the point 1, 2, negative 1. Whew! Okay, that looks pretty good, I guess. Kind of easy enough to see in three dimensions. So, triangle representation or row echelon form using Gaussian elimination of an equation in three variables, needing three equations to solve it. All right, so let's go back to the beginning and look at what we did. We have three equations, and we used row operations to get rid of each term successively from the bottom two equations so that we got to a place where we could back substitute and solve. And each time we had to do a whole lot of writing all the way down. But notice, the values, right, the coefficients changed almost, at least one of the coefficients changed every step of the way, but the xxx, yyy, zzz was always there. We always just kept rewriting the variable associated with each coefficient every step of the way. So, an easier way to do exactly the same problem is to convert it to a matrix. And a matrix means to convert a system of equations. I'm going to write it all again. X plus 3y plus 2z equals 5. 3x plus y minus 2z equals 7. And 2x plus 2y plus 3z equals 3. If I wanted to convert this to a matrix, I could just put the coefficients in. So I could just write for the first equation 1, 3, and 2 for the coefficients. For the second equation, I could write 3, 1, negative 2. And for the third equation, 2, 2, and 3. And I denote that it's a matrix by putting it in brackets. Already my job is so much easier. And there are lots of things I could do to operate a matrix like this, but the truth is I needed these outside values, right? The constants included in my matrix when I solve, or excuse me, included in my equations when I solved them. So if we put a row of constants in, we call this a augmented matrix. Okay, so there are two kinds of matrices here that we have the matrix that includes only the coefficients, called the coefficient matrix. And we have the matrix that includes all of it, including the constants on the other side of the equal sign, and this is called the augmented matrix. And I got to get me some more room here. All right, a little note about the augmented, this dotted line, it's just a helper step. Later on in life, you won't put that dotted line in, you'll just write 4 rows and you'll know that the first row is the x variable, the second row is the y, third row is z, and the fourth row is the constant. You'll just know that. But in the meantime, it's kind of convenient to put the dotted line there to remind you that it's an equal sign. All the same rules, the Gaussian elimination method, all the same rules apply and the same strategy applies. So let's do this very same matrix, only this time we're going to do row operations on the matrix rather than the equation. Now we already know the answer, but I just want to show you it's doing exactly the same thing. First thing I want to do is get rid of this value here, so I'm going to change the third row by adding -2 times row 1. I'm going to write down all the rows that aren't changing. And then do my changing. 1 times -2 is -2 plus 2 is 0. 3 times -2 is -6 plus 2 is -4. 2 times -2 is -4 plus 3 is -1. 5 times -2 is -10 plus 3 is -7. Done. And let's look up here, and you should see that we have 0, 4, -1, -7, 0. Uh-oh, did I make a mistake? 0, -4, -1, -7. I did not. 0, -4, -1, -7. Okay, now I want to take out this value, so I'm going to change row 2 by adding -3 times row 1. Again, not changing the first and third rows. Oh, I forgot. I'm going to have a hard time with that because I never learned it when I was coming up. Okay, so now let's put in the values, or the middle row. 1 times -3 is -3 plus 3 is 0. 3 times -3, -9 plus 1, -8. 2 times -3, -6 minus 2, -8. 5 times -3, -15 plus 7, -8. I want to change this row so I get a 1 here. So I'm going to just multiply it by -1/8. So the rows I'm not changing, 1, 3, 2, 5. Changing the middle row, 0, -4, -1, -7. And now let's change the center row. -1, whoops, I'm multiplying by -1/8. So 1, 1, 1. Last thing I want to get rid of is this -4. So I'm going to add 4 times row 2. Okay, the rows I'm not changing, 1, 3, 2, 5, and 0. I don't need the 0 anymore. -4, -1, nope, that's not the one. 1, 1, 1. Now I'm going to change my third row. So let's do it. 1 times 4 is 4, minus 4 is 0. 1 times 4 is 4 minus 1 is 3. 1 times 4 is 4 minus 7 is -3. So if I convert this whole thing back into equations, I get 1 times x plus 3y plus 2z equals 5. Oh, I told you I'm going to be bad about that. And it's okay with me if you're bad about that. I don't need you to put the dotted line in there unless you need it or want it. Second row is going to be y plus z equals 1. And the third row is 3z equals -3. And if you look, that's exactly what we ended up with up here. And when we did our back substitution, we ended up with our answer. Our value is that the solution is the point x equals 1, y equals 2, and z equals -1. Done.